Alright, what's going on everybody? Today we're going to be doing another LeetCode problem. This one's called copy list with random pointer. It's a medium, so it's another list problem. Let's get into it. So we're basically just given a linked list. There's a huge explanation here, but long story short, we're given a linked list, and it's basically like a regular linked list, except in addition to the next pointers, so regular linked list and these LeetCode problems has like an integer value and then a next pointer which points to another node, and so on and so forth. But this linked list that we're given also has a random pointer in addition to a next pointer, and the random pointer points to either null pointer or it points to any other node in the list, right? So they basically want us to just return a deep copy of the list they give us, and it needs to basically be exactly like the list they give us, right? So first, I'll go over the naive approach. So the naive approach involves a linear space solution. So we're going to use a hash map basically to do two passes, because we can't really do this in one pass, right? Because if we were trying to assign the random pointers at each node, like imagine we were at this node here, if we tried to assign a node to the random pointer, we wouldn't be able to do that because we haven't even created, like for this node, we obviously haven't created, like this random pointer points to null. Well, that's a bad example. Let's take this node, right? So the random pointer points, let's see, to this node, right? But it hasn't been created yet, so we can't do that. So we need to do it in two passes at least, right? So for the naive approach, we're gonna have linear space. There is an optimal approach which has O of one space, so you can skip to that if you don't want to watch the naive approach, but I'll just code up the naive approach real quick first. So there's going to be two passes for the naive approach. The first thing we're going to want to do is basically just we're going to use an unordered map, right? So that's just a hash map in C++. So we're going to have an unordered map of where the key is a node pointer. The value is also going to be a node pointer. So we're going to treat the key node pointer like it's going to correspond to the node in the original list, and then the value will correspond to the node in the new list we're creating, and the key values will map those lists so that they are kind of we're able to take a node from the original list and then see exactly what node in our new list that corresponds to. So I'm just going to call this map. We also want a node pointer for traversing the original list, so I'll just call it cur, and we're going to say while cur, right? So while that node is not null, we're just going to move down the list. So in our first pass, we're just going to initialize a bunch of new nodes. We're not going to worry about assigning any of those pointers yet. We'll do that in the second pass. So first pass, we're going to create, so node star, and I'll just call it in, or I'll call it copy, because this is going to be the new node that we're copying, and we're going to say use a keyword new and node, and we can see the constructor here. There's only one constructor and it takes the value. So the value we want here is going to be the current value, right? So that's our new node, and then in our map we can say the key is going to be that current node, and it's going to map to the new node we just created, and then we can just slide down the list by assigning cur to that pointer to cur next. So that's the first pass. We just initialized the allocated space for all those new nodes. Now for a second pass, let's just set cur back to head, and we're gonna do the same thing. We're gonna iterate while cur is not null, and then we're going to basically deal with assigning those pointers now. So our map at the current node, the next node, so right, this is going to be the value at map cur, which is going to be that new node we created. So its next node is going to be assigned to the whatever the pointer is to the current next node, right? So that's already been initialized, that value. So we're going to assign that, and then we're going to do pretty much the exact same thing for the random node, right? So current random, so that's going to be the new node we created. Its random pointer is going to get assigned to the whatever that pointer is, to the node we initialized corresponding to that current random pointer. So that's pretty much it there. We can just move down the list at each iteration, like same way we did in the first pass. So cur is equal to cur next, and then at the end of this, the beginning of the list will just be we're going to want to return, right, because it takes a pointer to that new list we created. We're going to return map at head, and then that's pretty much it for the naive approach. It's going to be, again, the time complexity of this is linear, and then the space complexity is also linear. So I'll just submit this and verify that this code works. So the time complexity and space complexity, really we're looking at the space complexity here. It's not very good, beats 35%. We can actually do this in constant space, so we don't have to use a hash map here. It's a little trickier, so I'm going to whiteboard that just to kind of show better how it works. But if we analyze the complexity here, it looks like we can't do that, but anyways, yeah, this is going to be linear space, right? Because we're using this hash map and it scales according to how many nodes are in this list that we're given. So so this is again, big O of in space, but we can do better, right? So let's get rid of this and let's whiteboard the algorithm basically for the O of 1 solution. So for the O of 1 solution, O of 1 space solution, we're going to have 3 passes, right? 3 passes. Our first pass, we're basically going to copy the nodes in the original list, and we're going to interleave them into the original list. After that, we're going to deal with assigning the random pointers, and then the last step will be to separate the 2 lists. So it's a little bit tricky, but hopefully it makes more sense after the whiteboarding. So I'm just gonna make a random list here, random example. So we'll have 3 nodes here, 1, 7, just giving these random values 5, and then of course the last node will just point to null. So this is our original list, pretty standard linked list, except we have random pointers, right? So let's just say this 1, these dash lines will correspond to the random pointers. So let's just say that the random pointer for 1 points to 5, for the 7 we'll make this one the null pointer, so that'll be null, and then we'll just say this 5 points back to the 1. So this is this would be the list we're given, right? So so let's go through the algorithm step by step. So for the first pass, let's just let me get a color here. So we'll say pass number 1. So I'm going to keep this just so it's a little clear like where we are in our algorithm. So for our first pass, we're going to basically make a copy of each of these nodes, and we're going to interleave them into the original list. So basically what we want to do first is we're gonna have a current pointer, and it's gonna point to the first node in the list. So we'll have a current pointer, it'll be here, and we're basically going to, first thing we're going to want to do is preserve the rest of the list. So we're gonna create a pointer, a temporary pointer that'll point here. So we'll have a temporary pointer T, it'll point here. Now we want to create a new node that's basically a copy of this first node, right? So this is just one iteration of this first pass. So we're gonna create a new node here. It'll have the same value as that one. And we created a pointer that's preserving the rest of this list, so we can safely repoint this pointer here for current. So instead of pointing here, this is gonna point to this now. And then what we can do is we can point this new node we created to whatever this temporary pointer is pointing to, which is going to be that next node in the original list. So after that, we can just shift our current node down to that temporary node and then repeat that process over again. So our current node is going to be there, and that's the end of one iteration. So let's go ahead and do that again. So we're going to have a temporary pointer that points to the next node in the list. So T there. Now we can create our new node here. It's going to have the same value, right? It's just a copy of this node, and we can safely repoint this arrow. Now this pointer, we're going to assign it to that new node we created, and then point this new node's next node to the next node in the original list, and then we can slide this current pointer down. And we're gonna do this while current is not null. So that's another iteration. So our temporary pointer will point to this now, which is fine. And we're going to create a node copy of this 5. So that'll go here. And we can safely repoint this arrow. So erase that. This will go here. And then we point the 5 to whatever temporary is pointing to. And then we can shift current down. And now current is null, so we're done looping, and that's it for the first pass. So basically what we did is we created all these new nodes and we just interleaved them within the original list, right? So for the second pass, we're gonna handle the random pointers. So let's go over the step by step for the second pass. So basically the first thing we're going to want to do is set our current pointer back to the head of the original list. So let's do that. So our current pointer is going to point here again, and we're going to want to first check if our if the node we're at in the original list, if its random pointer is actually pointing to a node. If it's not pointing to a node, if it's null, we don't have to do anything, because by default, these new nodes we created, the random pointers will point to null. So we'll first check if the current node's random pointer exists. And if it does, basically the logic here is we're going to set the current node's next node's random pointer to whatever the current node's random pointer's next node is, right? Because the next node of the random pointer corresponds to that node in the original list. So hopefully that makes sense. I'll go over that process for each of these nodes just to show how that's going to work. So the current node's next node's random pointer, right? So this is the copied node, is going to be set to the current node's random pointers next node. So this 1, the random pointer will get set to this 5, right? And as you can see, that corresponds, this 1's random pointer points to the 5. So that's how we're going to do that. And then we can just simply say current is going to be current next, right? Because we want to do the same process for the next node in the original list. So let's slide that current pointer down. Okay, so then we basically do the same thing. So we're going to check if the current node's random pointer exists. It doesn't, it's null, so we don't have to do anything. We can just set current to current next, because this really is already pointing to null by default, right? So that's why we don't have to do anything there. So we're gonna move current down to current next. So current will be here, and then we're gonna ask, does the current node's random pointer point to something? Yes, it does. So the current node's next node's random pointer will be set to the current node's random pointer's next node, which is 1. So this is going to point here. Okay, so that's pretty much it, because when we slide current down to current next, current will be null. At that point, we're done looping for the second pass. All right, so we've handled the random pointers. As you can see, it pretty much exactly corresponds to the original list, but we have this issue where we modified the original list, right? These pointers are pointing to the copied nodes, and likewise the copied list nodes are pointing to the original list. So we're gonna have to separate them, right? That's gonna be the last step for pass number 3. So let me just clarify this. So we're now on pass number 3. We're gonna separate these lists. So the first thing we want to do before we start looping is create a dummy node, right? Because we want to keep track of basically the beginning of the original list. So, or not the original list, but the new list. So we're going to create a dummy node here. The value doesn't matter, so I'm just going to, we still have to pass in a value because the constructor takes an integer value, but anyways, it doesn't matter. We'll just pass in 0, and I'll denote this with D. So we have this dummy node. We're gonna have our current node is going to point to dummy at first. So our current node is gonna point to dummy, and the first thing we're going to want to do, well, first of all, we're gonna loop while head is, because we're also going to use our head node. We're going to use our current node to traverse the copied list, and we're going to use our head node. We'll just recycle the head node to traverse the original list. So our head pointer is going to point here at first, and we're going to loop while head is not null, and we're going to basically just separate these lists. So the first thing we want to do is basically set we want to set current, whatever current is pointing to next needs to be whatever head is pointing to next. So the current node at first is this dummy node, and it's going to point to whatever head is pointing to next, which is the beginning of our copied list. So this will be the first thing we do. And then we want to slide the current node down, right? Because basically the first thing we want to, the first basically part of this iteration is going to be to handle the copied list, and then we're going to go ahead and handle the original list. So and this is just one iteration. So So this dummy node will point to the beginning of the copied list, and then we're going to slide the current node down by pointing current or assigning the current node to current next. So current will go to this node. Okay, and then we're gonna handle this original list here. So head, whatever head is pointing to, so the next pointer for the head node is going to be set to head next next. So we can take this pointer and move it here. And in doing that, we separated the we're beginning to separate this original list. So, and then we're going to slide head down by setting head to head next. So head will now be here. And that's one iteration. So again, we're going to set the current node, the next pointer is going to get assigned to whatever head is pointing to next, right? So that goes away, and then this goes to head next. Okay, and then we're going to slide our current node down by setting current equal to current next. So current will be here, and then we can erase that. So then we're going to handle the original list. So whatever head, so head next is going to be pointing to head next next. So this will get pointed to here, and then we're going to set head to, or we'll set head to head head next. So that goes away, and then head is going to be here. Okay, so again, so another iteration. So current next is going to be set to whoever head's pointing to next. So this goes away. That goes there. And then we're going to slide the current down to whoever head is pointing to next. So current will be here. And then we'll assign head next to head next next. So this will point here, and then we move head to head next. And again, we're looping, we're doing a while loop while head is not null. So at this point, we're done iterating, and we just need to deallocate this dummy node and basically return a pointer to this first node, and we're done. So we're gonna basically deallocate this and then just return a pointer to this, and that's it for the algorithm. So hopefully the whiteboarding helps clear up some confusion, because the algorithm is a little tricky for the O of 1 space solution, but there's no extra data structures here, so it's pretty efficient. It's basically the most optimal solution you can derive for this problem. So let's go ahead and get into the code. So the first thing I'm going to do is basically, we can have, like, if we look at the description for this problem, we can have potentially 0 nodes, right? So that would mean head is null. So just to speed up the that edge case a little bit, I'm gonna just have a if statement here. If head is a null pointer, we can just return null pointer, right? Because that would be the copy of that list that contains 0 nodes. So the next thing we're gonna do is just get into the actual bulk of the algorithm. So the first pass, we're basically gonna interleave copied nodes into original list. So that was like the first pass we did. So in doing so, we need a pointer. I'll just call it cur. It'll be the head of the list at first. And then we're gonna loop while current is not null, right? Just to get through that entire original list. We want to have a temporary pointer to preserve the rest of the list, right? So I'll call it temp, and I'll point to cur next. Okay, now we can make a deep copy of that current node, right? So to do that, we'll just say current node start copy, use that new keyword node, and then we see the only constructor here for node struct takes a val. So, and we know the val is going to be whatever the value is for current. So we just made a deep copy of that node that we're at. Then we can go ahead and assign the current next pointer to that deep copied node. And then we can point that deep copied node's next pointer, we can assign that to that temp node, right? Because that's the next node in the original list. And then we want to just shift our current pointer down, so we'll set current equal to temp to move to the next node in the original list. So that's pretty much it for the first pass, right? We basically just interleaved a bunch of deep copied nodes into the original list. So the next step is going to be to handle the random pointers, right? So we'll just say assign random pointers for copied nodes. So we're going to set that current pointer back to the head, just to get back to the start of the list. And we're going to say while cur, right? So we're going to loop while that current node is not null. We want to first ask, right, if that current node's random pointer exists. So if current random, as long as that's not null, we can actually bother assigning it. So the way we do that is, it's a little confusing, but not too bad if you pay attention to the whiteboarding. So the current next, right, because that's going to be the deep copied node. So current next, that random node is going to get assigned to the current random node's next node, because that's the random deep copy. So that's basically the way we do that. And then we can slide down the list because we want to go to the next original node, right? So current will be current next to skip that deep copied node. So that's how we're going to handle the random pointers. So that's the second pass, and then we just have one more pass, right, where we're going to separate those lists, right? So we're going to restore the original list and then separate the new list we made so that it's by itself, because we obviously don't want to modify what's getting passed into a function ever, right? Because that can create unpredictable behavior. So we need to restore the original list, and we need to separate the new list. So we'll do that in the third pass here. So we're gonna make a dummy node. So and I'll make a note of this. So separate the list, restore original list, right? Because that's important. So we're gonna create a dummy node. So node star dummy. We're gonna need to allocate space for that. So new node. And we can just pass in any integer value there. It doesn't matter because this is really just a placeholder to keep track of the list we made a deep copy of. So we're going to restore that. So we're going to create that dummy node, and we're going to set that current pointer to our dummy. And we're basically going to loop while head is not null, because we're going to use head to traverse the original list, and we'll use cur to traverse the deep copied list. So So we'll head, and we're basically gonna just, the first thing we'll do is handle the separating of the deep copied list, and then we'll handle the separating of the original list. So separates new list. So to do that, our current, the next, the current next will get assigned basically to whatever head is pointing to next. Right, so that's like the original list node. And then we need to slide down the new list. So we'll say current, we'll change that current node to current next, right, to move down. So then we're gonna separate the original list. And to do so, we're gonna set head next. So that next pointer is gonna get assigned to head next. We need to skip nodes, right? Because we're taking the original list and we're skipping over that the copy node we inserted, basically. And then we need to slide down or shift down that original list. So head is gonna get set to head next to just keep traversing that original list. So that's pretty much it for the third pass. So after that, those lists will be separated. And what I've seen a lot is that people just return dummy next in these list problems, and like you can't do that because every time you use this keyword, you've got to deallocate the space that you allocated, right? Otherwise you have a memory leak. So if you're calling this function a lot, like that could get really bad. You don't really want memory leaks ever. So before we do this, we basically need to deallocate that space for the dummy node, right? So we're going to, the way I'm going to do this is I'll recycle that current node. I'll set that to dummy, and then I'll just shift the pointer for dummy down to the head of the copied list. So we'll say dummy is equal to dummy next, right? That'll be the head of the copied list. Then we can use the keyword delete on the current node. That'll basically deallocate that space for dummy node. And now we can safely return dummy without any memory leaks. And that's pretty much it for the algorithm. So prevent mem leak. So that's pretty much it for the code for the O of 1 solution. So this is a O of 1 space. Obviously the time is going to be linear because we just have a bunch of for loops. Technically it's like 3 in time complexity, but of course in big O notation that just simplifies to big O of n, or linear time. So let's go ahead and submit this just to verify that the code works. So as you can see, runtime 90%, that's good. About the same as the naive approach, but what's better is the memory. So we beat 60% for memory, and it can probably beat up to 90%. Beats 97%. It's a pretty efficient solution. I'm pretty sure it's the most optimal solution you can have for this problem. So hopefully this video helped you understand it better. If it did, leave a like and subscribe. It helps out the channel. So thanks, and I'll see you guys in the next video. Peace.